Hi, we are from Group 9 and we'll be explaining motion using kinematics and dynamics using satellites in space. So, our group consists of YiJia, Javier, HaoZhi, FanCheng, and me, myself, Kiat. So, why using satellites? Because satellites is very costly and is an important technology to keep the world connected. So, our internet, our phone, it requires satellites to communicate with each other around the globe. So, for example, a weather satellite costs 290 million. A spy satellite costs roughly 390 million, and the yearly usage cost in millions also is 1.5 million, and to launch it, it costs as much as 400 million. So we have to protect all these satellite and this technology and calculate their movement. So the purpose of the project will be studying the motion of the satellite to keep it floating in the space and orbit around Earth. So the study of the motion will prevent satellites from collision. As we humans have been sending satellites into space, the satellites have been congested with many satellites, rockets, body, and other many space debris. So in order to know the motion of satellites, we have to understand the relationship between velocity and gravitational force. So how satellite gains in momentum? As we know, momentum is equal to the mass times velocity. So the mass is equal to the satellite mass, and the velocity is gained from the ejection of the rockets. So we have to know how fast we have to launch the rocket and send the satellite into space, as this velocity will be used, will be transferred to the satellite to move and orbit around the Earth. So the satellite loses its momentum. Satellite will stay in motion for a very long period of time, as friction in space are negligible. So velocity remains almost constant throughout. So gravity and velocity keeps the satellite in a circular motion, which causes a centripetal force, and satellite will move around the Earth and orbit. So we'll go into details in circular motion and centripetal force.
To better understand the motion of an orbiting satellite, the motion can be described by the same motion characteristics as any object in circular motion. For motion in a circular of a radius r, then we can get the circumference of the circle, which is c equals to 2 pi times r. Then if we assume the period of this rotation is t, then the angular velocity omega is omega equals to 2 pi over t, or 2 pi times f, or delta theta divided by delta t. So we can get the speed of the object traveling the circle, which will give us v equals to 2 pi r divided by t, or omega squared times r. So we can derive the acceleration due to change in the direction, which is v squared over r, or omega squared r. So the acceleration, which is produced by a centripetal force, and it is also constant in magnitude and directed towards the axis of rotation. So by using Newton's second law, we can get the centripetal force of an object with mass m is equals to mac, and it also equals to mv squared divided by r, and also mr omega squared. So after understanding the circular motion, we can now using this model into the study of the satellite. So during the movement of the satellites, the centripetal force is supplied by gravity, which acts at a distance between any two objects that have mass. So just the picture here show the acceleration is directed towards the axis of rotation, and the velocity is tangential to the orbit. So we can consider a satellite with a mass m satellite that orbiting central body with a mass of m central. So by using the equation I have derived above, the total force is m satellite times v squared divided by r. And also, we know that the centripetal force of the satellite is given by the gravity. So we can express gravity as gm satellite times m central divided by r squared. We can let equal these two equations, then we can derive the v of the satellite, which is square root of g times m central divided by r. So by comparing the centripetal force required and the gravitational force experienced, we can estimate whether the satellite is able to stay in circular motion. So if the centripetal force required, which is given by the equation on the left, is bigger than the gravitational force, then we can say that gravity is not allowed to hold the satellite in its orbit, so it will drift out of the orbit. And in another scenario, if the net force is smaller than the gravity, then it will collapse into the Earth. So after we have established our circular motion model, then we can verify it with this equation. Here is the actual scenario. This is a real satellite, Navstar 66, and we can substitute the mass of Earth into the equation to substitute the m central, and we can take the average value of apogee and perigee to represent r. After calculation, we can get the v in theory is 4 kilometers per second, and we can also obtain from this picture here that the actual velocity is actually 3.89 kilometers per second. It's really close. So we can conclude that our model really fits in the motion. But just the picture here shows, there are other cases where the circular model does not fit the actual data, which suggests that more universal model is needed.
Okay, so in the actual scenario, the satellites always move in the oval orbit, which means that the force is not completely vertical to the direction of the motion, showed like the picture on the left. So it is more complete, it's more complex for us to analyze the motion. So I will give some of the examples. When the satellite stays at the position which is moving away from the Earth, the gravitational force A1 can be divided into A1 prime and A1 prime prime. So the A1 prime is inverse the moving direction, which means that it provide negative work done and slow the satellite down. And the A1 prime prime is vertical to the moving direction, and it can change the direction of the motion of this satellite. And when the satellite is moving toward the Earth, the gravitational force A2 can be divided into A2 prime and A2 prime prime. The A2 prime is vertical to the direction of the moving, so it can change the moving direction, and the A2 prime prime is same as the moving direction, so it can speed the satellites up and to give positive work done. And for the satellite which reaches the end of the long axis, the gravitational force A3 and A4 is vertical to the moving direction, and at this time it cannot be divided into two forces, and it can only change the moving direction, which means that at the end of at this situation, the satellite is moving according to the circular motion.
Now I'm going to show you about the program used to simulate the movement of the Earth satellite. This program takes in the perigee and apogee, which means the nearest and farthest point that the satellite is away from the Earth. The first one I'm going to show is a geostationary satellite, which means it has the same angular velocity as the rotation of the Earth. This circle stands for the Earth, and this circle stands for the satellite. we can see that the satellite runs in a circular orbit and it runs at a constant speed. This satellite has an ellipse orbit, and we can see that it moves fast when it is close to the Earth and moves slow when it is far away from the Earth. This is a major part of the program. It figures out the velocity at every instance. The total energy of the satellite is considered constant, and it consists of gravitation potential energy and kinetic energy. The total energy of the satellite is given out by this formula, and the potential energy of the satellite is given out by this formula. A is a constant number for every ellipse, and R can be figured out according to its position, so we can figure out the velocity of the satellite at every point.
Okay, by learning kinematics and dynamics and how it is used in satellites, we can use it to explain other use cases, such as avoiding satellite crashes, binary star systems, and planet satellites. So, there are many satellites in space right now, and how do scientists know if they can launch another satellite or if the satellites will not interfere with each other? They can use this method of calculation to figure out if the satellites will crash, because the radius r, nothing in space is affected by friction, gravity. Is in an ideal environment, so calculations are more ideal than it is on Earth. Hence, their calculations will be more accurate and the error rate will be lower. So they can use this calculation quite accurately, and they can avoid satellite crashes better. So the other use case will be binary star systems. And what binary star system is if you look on the diagram to your left, right? There are when two planets are in orbit with each other with a center of mass in space. This center of mass will determine the radius between the center of mass and the planet will determine its velocity. And this velocity is constant throughout, because there's nothing else, no other force acting on it. So the velocity will be constant. What affects the distance r will be the planet's mass, because that will affect the centripetal force, and it will affect how fast or slow it will go as well. So if you can see on the left, the diagram, right? Say we have two ideal planets with the same mass. Their orbits around this center mass O will be constant and will be the same velocity, same everything. It's just that they'll always be at polar opposites because they started at polar opposites. But their orbit, their period of orbit, their velocity all remain constant because they have the same mass. Okay, the other use case will be a planet satellite. Okay, if you can argue that the Earth and the Moon, right? Although they are not the same mass, they are relatively huge masses. So why does the Moon orbit around the Earth, but the Earth does not orbit around the Moon? And why does it not undergo a binary star system? Okay, basically, you can treat the Moon as a satellite because it's technically a planet satellite. So why is it not a binary star system? It's very simple. Because due to comparing the size of the Moon to Earth, right? Although comparing Earth's moon and other planets' moon, the moon of Earth is relatively larger compared to other planets' moon, compared to the other planet. The center of mass between Earth and Moon is still inside the Earth itself. Hence, since the center of mass is not in the middle or in space, the Earth does not undergo circular motion at all. Only the Moon does. So all in all, what affects whether two planets are in a binary star system is simply if the center of mass is in space between the two planets, or is it in one planet itself.